Okay, we're going to actually, as far as the textbook is concerned, take a few, take a step back, if you will. In the Stewart textbook, this is chapter 2, which we had just basically completed chapter 3. So you might wonder why we're doing this a little out of order. Well, our last topic that we'll be covering, which is chapter 4 in the Stewart book, is about the exponential and logarithmic functions. And to get us sort of thinking in that direction, I wanted to hold off on the last two sections of chapter 2 here. They cover, as this section here is combinations and compositions of functions, and then we'll look at inverse functions. Mainly here, what we're looking at is taking two or more functions and creating new functions with them. If you remember, we had started off with functions. We sort of had our 8 basic functions that we used, and we looked at how to translate those up, down, left, right, do reflections in the coordinate axes and vertical stretches and so on and so forth to create new functions. Now we're going to take 2 of those functions and combine them to create one new function. So we first start with combining functions, which is fairly simple, I think, in terms of what's going on here. We start with 2 functions. We're calling them f and g, and the domains respectively are a and b. So the domain of the function f is a and the domain of the function g is b, just so we can talk about the domains of our created functions down below. We name those 2 domains. And so here are the 4 functions. The first one is right here, and it's the function f plus g of x. And that's what we call it. Now, notice in the parentheses here, this is the name of the function. You might say, well, just adding, what's the big deal? Well, remember, the function is a rule or set of instructions, right? It's a relation that assigns each value in the domain to exactly one value in the domain. So how does this function do that? What's the process? So here's the name of the function. We input x, and how do we determine the output? Well, when I plug in x, the output is determined by taking the output to the function f and adding it to the output of the function g. All right, so that's the way this function works, right? For 2 different functions f and g, we define the function f plus g of x. So that seems pretty natural in terms of why we would call it f plus g. Now the domain has, what is this, a, and what's this symbol? This symbol is the symbol for an intersection. And so what does that mean? A intersect B, we say. This is basically the domain common to both A and B. So for instance, if A were, say the domain of A was everything greater than 0, and the domain of B was everything less than or equal to 1, then the common overlap between those two, what's common is what? Everything greater than 0, everything less than or equal to 1 would be everything greater than 0 but less than 1. Right? It would just be that small domain would be the domain for the new function. So basically it's just it has to be whatever works for both the function f and g. Okay, similarly we have the function f minus g of x, and you can see how that's defined, simply subtracting the outputs of the 2 functions. This is fg, or f times g of x. Right, we just write f and g together like that with no symbol. And so we multiply the outputs together. And notice the domains in each case are the same. It's the common domain, if you will, for both the functions f and g. And then this is f, and it looks like /g, or f divided by g. Sometimes it might be written this way in a fraction form like that. So what is this? This is dividing the outputs, f of x divided by g of x. Now, the domain here is as above, and it's kind of, what is all this about? This is the set of what? All x. This symbol, I don't know if you've seen this before, but this is an element of, or is a member of. So x is in what we talked about, the intersection of a and b. So all this is saying is that we're looking again like the domains above that are values in the domain common to both the functions f and g. And then this vertical bar means such that, or given. And so there's one little restriction in this case, and that is the g of x function cannot have an output of 0. And that should make sense, because then we would be doing what? We would be dividing by 0, which is undefined. And so we would exclude values of x in the domain of G where its output is 0. Okay, so let's put this to practice and do several examples. It's not that difficult. You will need to review a little bit in terms of simplifying some of these expressions, and so we'll be doing some of that as we look at these examples. So let's take a look at this first example, and you can see we're going to find each of these expressions we've talked about above and give their domains as well. So let's look at the first one here, f plus g of x. So again, the definition says that's simply f of x plus g of x. Well, what is the output to the function f of x? Well, here it is, right? Whenever we plug in x, the output is square x, add x to the squared value, and then subtract 6. So I'm just going to sort of put that in parentheses here. And then plus g of x, and g of x is what? X squared minus 4. Okay. So there it is, and now that's the rule, yeah, but we would like to simplify if we can, and so I hope you see that we can do that by combining like terms. And so we've got x squared plus x squared, 1x, and then negative 6 plus a negative 4 is negative 10. So there's a more compact way, and that's the way you should write that. So there is the function f plus g of x. There's its rule. And what about the domain? Okay. Well, let's talk about the domain of the original two functions. What's the domain of the function f of x? What's the domain of this function? Are there any values of x that result in an undefined expression? Are we ever dividing by 0? Are we ever taking the square root or an even root of a negative number? No. Right? In fact, this is a quadratic function, and we know from quadratic functions that the domain is all real numbers, right? Any value of x can be plugged in here and we'll get a real output. Same thing here, right? Both of these are quadratic functions, and so the domains for each of these is all real numbers, which we can write that way in interval notation, right? And so in this case, the common overlap between the domains is the same, right? Since the domain for both is all real numbers, and the domain for this is all real numbers. Okay. So not a very much to do there. Okay, now let's be careful when we go to f minus g of x. Of course, f of x minus g of x. And now you might wonder, why did I put this stuff in parentheses up here? Did I really need the parentheses up here? No. I mean, I could distribute the 1 through and we'd be done. But be real careful here. I'm going to put the parentheses again. And it's minus, right? And so what you got to be careful about, right, is to make sure we distribute through, right? The distributive property, right? Negative 1 times x squared, negative 1 times 4. So just be careful about that. That's a common mistake. So this becomes plus 4. And now we can combine like terms. And what do we get? I get x squared minus x squared. Well, there's no x squared terms. I have 1x. And I have, what, negative 6 plus 4 is negative 2. So this is f minus g of x. And the domain, like above, is all real numbers. Let me just say something real quick about something. Now, in each of these cases, we're finding these new functions. What if I just throw this in here and say, well, what is f minus g of, say, 3? That's f minus g of 3. What if I ask for that? Well, you know, obviously we just found a rule for f minus g, right? So I can now use this rule and plug in directly, right? So what do I do for the function? Wherever I see an x, I'm going to replace it with 3. And very easily, 3 minus 2 is equal to 1. So now we did the work, and we've got this rule, if you will, for this function, how to determine the output to this function, and we can use it. But what if I hadn't done that? Could I have found this expression in another way? Well, I mean, Yeah, I mean, what is f minus g of 3? It's nothing more than f of 3 minus g of 3. Okay, now what is f of 3? Well, now I'm going to plug into the function up here, f of x, which is x squared plus x minus 6, replacing x with 3. 3 squared plus 3 minus 6. So what do we get here? We get 9 plus 3 is 12 minus 6, we get 6. And g of 3, well, what's g of x? G of x is x squared minus 4, so I replace x with 3. I get 3 squared minus 4. That's 9 minus 4, which is 5. And so I get 6 for this output, 5 for this output. 6 minus 5 is 1. We say, well, that's dumb. Why did I go through all this trouble? Well, I'm just saying, the point is, if you want to evaluate any combination, f minus g, f plus g, f times g, whatever, at a particular value of x, you could certainly find the formula like we've gone through here and then do that, or you could circumvent getting the formula if this is all you need, f minus g of 3, just by finding whatever f of 3 is, whatever g of 3 is, and taking the difference. Now, finding the formula is nice because especially if you have to evaluate the function at many different values, right? You need to evaluate it at 3, 4, 5, and 6, and so on, then we can quickly compute those quantities with this formula. But sometimes the work to simplify might be a little bit more, and if you just need this value, this would be a quick way to go. So be careful on the test. If I ask you for f minus g of x, all right, we're looking for this. If I ask for f minus g of 3, make sure you give the correct output. All right, we also want to look at f times g of x, or fg of x, right? So that's taking the value of f of x times the value of g of x. So the value of f of x, again, was x squared plus x minus 6, and the value of g of x was x squared minus 4. Okay. And there's the answer, right? And that's certainly fine to leave it in that form. Now, if you're checking your work, like in the book or something, a lot of times what they'll do with this is they'll expand this out and combine like terms. Okay, so I just want to review that with you. It's a good opportunity to review multiplication of polynomials. So how do we multiply a 3-term polynomial, right? A trinomial times a binomial. Basically, every term in this trinomial, each of these 3 terms, has to get multiplied by each of the 2 terms in this binomial. So I'll have 3 times 2, 6 multiplications. So if I multiply this all out, what do I get? Let me just do it this way. X squared times x squared plus x times x squared plus a negative 6 times x squared. So there I've multiplied each one of these by the x squared. And then each one of these times the negative 4. And it doesn't matter the order I necessarily multiply these in, just as long as each term in the trinomial on the left gets multiplied by each term of the binomial on the right. And now we go ahead and multiply these together. Remember how we do this when we multiply like bases to different powers, we add the exponents. And negative times negative, positive down here. And can we combine any like terms? Well, just 2, right? Just the x squared terms. So in all its expanded glory, we have this. Okay? So there's, certainly this is an answer, but if you look in the back of the book and you see this, then you need to make sure that you understand how to go from here to here and how to confirm. Okay. Again, the domain here is going to be all real numbers, as it was for the previous 2, as we've discussed already. Okay, so we'll write this as fg of x. Okay, now one more to go, and that was f divided by g of x. Let's take a look at that. All right, this way. This is f of x divided by g of x. And f of x is just x squared plus x minus 6. G of x squared minus 4. Now, let's talk about this function for a minute. What about domain? What would its domain be? Well, the domain we said was common to both f and g, which each one had all real numbers as their domain, so we're saying all real numbers. However, we can clearly see some values of x, I hope, where this thing is not defined. Right? In other words, what are the zeros of this polynomial down here? Well, we can factor that, and let me go ahead and do that. That's just the difference of squares, right? X plus 2x minus 2. Okay. And so right away we can see the domain cannot include what two values of x? Negative 2 and positive 2, right? Because we would be dividing by 0. So the domain would be all real numbers except for those. All right. So we would have to exclude those two values. Now, I factored the bottom. This is the answer, right? But could we simplify this? So how do we simplify a rational expression? Well, if there's any common factors, we can simplify a little bit. And so x squared plus x minus 6, does that factor? Can you factor that? Looking for a product of, since the coefficient in front of x squared is 1, looking for a product that's negative 6 but adds to positive 1. I think we can do that, can't we? 3 and negative 2, right? If we FOIL this out up top, we're going to get x squared plus x minus 6. And what happens, notice, is I have this common factor of x minus 2, which we can then simplify because x minus 2 divided by x minus 2 is equal to 1, right? And so, in a sense, I can simplify this this way. Now, let me just notice, go back to our domain. The domain was all real numbers except for what? Plus or minus 2. Now, when I look at the final simplified form, if I just gave you that and said, what's the domain of that? You would say what? Well, just x cannot be negative 2. Because x can now be 2. If I plug in 2, I get what 2 plus 3 is 5 divided by 4. I get 5/4. Right? Does that mean the domain is all of a sudden changed to just excluding negative 2? No. The original function, the domain, is still the same. And we've simplified this. Now, a lot of times when we're doing a simplification like this, notice we lost the information that x cannot be 2. Of course, x cannot be 2 in this expression because we would be dividing by 0. But for all x not equal to 2, we can do this cancellation. So sometimes we emphasize that by putting comma, x cannot be equal to 2. Just to emphasize that the two expressions are equal only for values of x not equal to 2. But again, so be careful about finding the domain after you simplify. The idea is to take a look at what you have initially first before you simplify to see what restrictions on a domain that may imply. Okay? All right. Let's take a look at another example. So we got two functions, f and g. Let's talk about domains now. Let's start with the function g of x, actually. That's just a linear function, 3x minus 1. The graph is what? A line of slope 3, y-intercept negative 1. So we know the domain is all real numbers. But what about the other function? Now, f has a radical square root. What do we know about the domain there? we're looking at real valued functions, meaning the outputs are real numbers. And so the output to this function is only going to be a real number of what? What I'm taking the square root of, which is 2 minus 5x, is what? What does it have to be? It has to be non-negative, greater than or equal to 0. So we can be equal to 0, square root of 0 is 0, but I can't be a negative value. Can't take the square root of a negative value. So notice the question is, what can x be though? So now I have this linear inequality. So you remember how to solve linear inequalities, right? Just like we do equations, I'm going to subtract 2. Just like linear equations, I'm going to subtract 2. And then I'm going to divide by negative 5. But what happens when I divide by a negative quantity with a linear inequality? Well, this inequality does what? Changes the direction, right? The sense of the inequality changes. Of course, negative 2 divided by negative 5, negative divided by negative is positive. And so what's the domain here? The domain is everything, any value of x less than or equal to 2/5, less than or equal to 2/5. So how do you write that in interval notation? All right, bracket on the 2/5, so we include, so any number less than or equal to 2/5. So that's going to be important, because when we talk about the domain of these functions, we talk about what? First of all, what's common to both? Well, what is common to both? These values are all contained in there, and so this smaller one, this is what's common to both. Notice I can't plug in anything greater than 2/5 into both functions. I can plug it into G, but I can't plug it into F. So the intersection of these two would be the smaller one, right? Since this one is sort of a subset, this interval is a subset of the original domain of all real numbers up here. Okay. So let's look at just finding f plus g of x first of all. Again, that's f of x plus g of x. And so here we've got f of x plus g of x. And I could put this in parentheses, but then when I distribute the 1, I'll just get that. Okay, and the domain we just talked about is everything less than 2/5. Right? Less than or equal to 2/5 rather. Okay, can we do any simplifying here? Like 2 minus 1, negative 5x, can I combine these in any way? No, because these are under the radical, right? So not a whole lot we can do at this point. I would say that would be our final result, right, for f plus g of x. So don't force the issue if you can't simplify it. Don't try and create something out of nothing, so to speak. Okay, let's take a look at f divided by g, and then we're going to look at g divided by f. Is that the same thing? No, we're going to see that's different. F plus g and g plus f will basically be the same thing, because addition is commutative, right? Same thing with multiplication, but division and subtraction is not commutative, so we get different functions. Let's take a look at f divided by g of x. That's f of x divided by g of x. So f of x was the function, the square root of 2 minus 5x. G of x is the function 3x minus 1. Okay. Now, let's talk about the domain. The common domain of f and g, indeed, is this again. So we start there. Are there any other restrictions? Remember, when we're dividing, we have some potential restrictions, right? We can't divide by 0, right? So I know that g of x cannot be 0, and therefore 3x minus 1 cannot be 0. Well, what value of x will make that be 0? If I add 1 and divide by 3, I see x cannot be equal to 1/3. Right, if x is 1/3, we've got a problem. And so, what's the domain? The domain is everything up to but not including 2/5, and then 1/3, excluding 1/3. Now, is 1/3 in this interval? That brings an interesting question. Do you know which is bigger? 1/3 versus 2/5. I mean, some of you know right away by converting to a decimal, right? 2/5 is 0.4. 1/3 is what? 0.333 forever. So 1/3 is less than 2/5. You can also do it by getting over a common denominator, right? So 1/3 is the same as what? 3 and 5. Least common denominator would be 15, correct? Because they're both prime. 3 times 5 is 15. So 5/15 if I multiply top and bottom by 5. And this would be what? Multiply top and bottom by 3, 6/15. And so clearly, you see that 1/3 is indeed less than 2/5. And that's important because this is everything less than or equal to 2/5, less than. So 1/3 would be in that interval. So we want to exclude 1/3, right? We want to exclude 1/3. And so how could we write the domain? So it's everything from minus infinity up to 2/5 and including it, except we have to exclude 1/3. So I'm going to go all the way up to 1/3. I want to exclude 1/3, so remember that's a parentheses. And I use my little union, right, symbol. Or what? Pick it up from 1/3 again, parentheses, up to and including 2/5 bracket. So notice the difference there on the domain with this particular function. Let's take a look at the other way, g divided by f of x, as we talked about. This is going to be a different function because this is g of x divided by f of x. Right? And basically we're just reciprocal, right? Just the reciprocal. G of x now is 3x minus 1, and here we get square root of 2 minus 5x. Okay, and again, not much we can do to simplify this. Somebody might say, hey, can we rationalize the denominator here? Yeah, you can, but I wouldn't do it. If they do that in the back of the book, that's fine. But I would just leave it like this in this case. What's the domain? Again, we had everything less than or equal to 2/5, but notice this time, right, if I plug in 2/5 here, what do I get under this radical? What do I get if I plug in 2/5? 5 times 2/5 is 2. 2 minus 2 is 0. I get 0. And that was in the domain of the original function f of x, right? Because, we can divide by, we can take the square root of 0, and we get 0. That's why we included 2/5. If I plug in 2/5, f of 2/5 is 0. But now, since I'm dividing by the output to f of x, I cannot divide by 0. So the restriction on the domain is simply to change it from minus infinity to 2/5, right? But this time we exclude 2/5 because that would make us be dividing by 0. Okay, so 4 new functions we can create from a given function, and how to think about the domain, especially in the cases where we're dividing one function's output by the other. Okay, in the next video what we're going to look at is a more interesting interaction between functions called function composition. And so we'll take a look at that in the next video.